Back to the class of drilling engineering. In the previous lecture, we talked about the functions of drilling fluids, and then we talked about the window of pore pressure versus the fracture pressure, and so on. Today, we'll discuss some of the main additives that we use in the drilling fluids to change its properties, and we'll see like what kind of equipments and labs equipments we use for the testing purpose in the laboratory. First of all, let's go and see what kind of drilling fluids we have. We said that we have three kinds of drilling fluid mainly, water-based, oil-based, and the foam-based. Let's see, foam-based is used only in underbalanced drilling, while in conventional normal drilling, we use sometimes water-based, sometimes oil-based. So let's look at it, what kind of water-based muds and oil-based muds we use, and so on. As I said, this gases and gas liquid mixture usually used in underbalanced drilling when we are dealing with reservoir zone only. This is the main structure classification of drilling fluids, where we have water-based, oil-based, and foam. And these four, the last four, used for the underbalanced drilling. These two are used for the conventional drilling and so on. Now, the liquids that we use, we can use the fresh water. When I'm talking about the water-based muds, so we can use the water as a continuous phase, okay, water as a continuous phase, or oil as a continuous phase. So what kind of oil, we will discuss that also. So when we say water as a continuous phase, then it should have some additives also, like solids or inactive soluble, and maybe some chemicals to avoid or inhibit corrosion, or maybe some other problems in the wellbore. So we have main fluid, which is water or oil, and then we have additives, solids, and we have to discuss what kind of solids we use there at the same time. So for the water-based mud, when sometimes we put some oil in this one. So when some drops of oil are added to the solid, the water, then it can create emulsification or emulsion mud. So this is not completely desired, but sometimes it is. But no, mostly we don't do that. We just use water-based or oil-based. So what kind of water we use? It depends on the availability. For example, you are drilling offshore and there is no fresh water. So what can you do? In that case, you have to use the seawater or saturated salt water. But sometimes the nearby, the well you are drilling, it is not the fresh water. Sometimes you have a brackish kind of a water. And sometimes you are drilling in the zone where you can drill the well and get fresh water very easily. So it depends like where you are drilling and what is the situation of water there. Then you can decide which kind of, then you design according to that. In the lab first, then you use in there also. Okay. Fresh water usually available on land locations, like places where they have easy to drill freshwater formations and so on. Chemicals are mostly solubles, chemical clays hydrate more. So when the clays hydrate more means they can emit the water and it all goes fine. Like it do not react with the formation and so on. Okay. Sometimes the disadvantage of fresh water may be the instability, borehole instability. And for that, then we have to use special additives to counter this kind of a problem. Then brackish or the saline or water, salt water, usually used in the offshore environment, or sometime in onshore where there's no fresh water available and nearby wellbore, the fresh water is not available. So we use the brackish, or it has usually high amount of calcium or magnesium. That's why we call it salty water. This one. And then we have seawater, total seawater. It has high amount of sodium chlorides and its hardness varies. So mostly this GOM represents the Gulf of Mexico, the offshore area where there's a lot of well, especially Norway area, Norway or UK. So they have this Gulf of Mexico and they drill offshore wells. There they are talking about chlorides, calcium, magnesium. What is the level of chloride, calcium, magnesium in those areas? So it's quite high. Chlorides are quite high. So when you use this kind of seawater, it's very hard to maintain the properties. And that's the job of the offshore drilling fluids engineer to maintain that kind of drilling fluids there. Okay. This saturated one, when you encounter the salt formation, you can use that one because it will be compatible with that. It will be almost the same. So it should be fine to work there and that point in the salt water. And usually used for clay inhibition. Then we use the KCl, calcium chloride, formulates, and so on, the brine water. But this is the least used. Mostly we use the fresh water or whatever brackish water is available, which has some sodium chlorides and so on. Then we have the oil-based mud as a continuous phase. This one is a bit expensive than water, as you know, is cheaper. You just drill the well and get it. Diesel has a cost. It's the same diesel, or we use sometimes synthetic-based oil as a continuous phase. Now this has a cost. Okay, but this one is bit better than the water phase. This one is more stable. Its properties under high temperature, pressure, this works better. When you drill deeper, maybe you can use this one also. Again, if you put some water in that oil, there will be some emulsions, and we do not want to react with oil. So as I said, the oil-based muds, it has a good amount of property at high temperature. At high temperature, for example, the water can evaporate. Okay, water can be steamed. But this oil actually, under high temperature, it can work well. Okay, and it has more inhibitive properties than the water-based mud. It's effective for all kinds of corrosion. So it has a lot of characteristics, but the problem is that it is a bit expensive than the water-based mud. So you see here the higher initial cost. Most pollution control procedures, because we have to make sure you clean it properly, and reduce effectiveness of some logging tools. So for example, you're trying to log the porosity of the nearby well, probably it may create some problem and so on. Detection of gas may be a bit more difficult because of gas solubility. So gas usually gets dissolved in the oil. So detection of gas kick may be harder, but still there are ways we can encounter solve this kind of problems. So overall, oil-based mud has a more promising result than the water-based mud. Now we will talk about it, like what kind of solids we are going to use with water or the oil. So basically, we have most common one is the bentonite. Is the most common bentonite, or we have another one which is the barite. These are the normal use. Then we have some more. This one, montmorillonite, colonite, chloride, and gumbo shell. So there's a lot of, you see in the next slides. We'll talk about them. As I said, the barite. So for example, the question could be like, okay, what is the additive that is used to increase the density of the mud? And why we want to increase the density of mud? Because sometimes the kick is occurring or blowout is happening. In order to counter that, we have to increase the density of the mud. So for that, we use the barite to counter that, and we can increase the drilling mud. It's the most common one and most cheaper one. Then we have hematite and calcium carbonate, mud density up to the. So most famous one is the barite one to increase the density of the mud. Then we have special low circulation materials, and the purpose of low circulation materials is, for example, if there are some fractures downhole, and whatever mud we are sending down, it is lost inside the formation. So when it is lost inside the formation, we need to use the low circulation material. Now, low circulation material actually is like a petrol jelly, the jelly, or let's say kind of a pudding kind of a thing that you eat at home. So that kind of a material, soft and still not penetrable, semi-solid, you can say. That kind of material it generates, jelly-like material. It goes down and settles in the fracture, and it does not let the fluid to get lost inside the formation. So we have a special low circulation material to counter the low circulation areas. It also depends on which kind of rock you are going to drill, sandstone, limestone, or dolomite. Then we have some more chemicals that we can add in drilling fluids. There are so many chemicals, for example, flocculant, mud thinner, you have acids, soda ash, starch, some of them are used to increase the viscosity, some of them used to decrease the viscosity, some of them, for example, are helping us to increase the mud cake, some of them help us to increase the gel strength, which is used to suspend the rock cuttings. So for the density, as I said, barite is the most powerful one, additive that we use. Weighting material are used to increase the mud weight. So if you want to thicken the mud so that it can handle the mud cuttings, so you can use the gypsum and sodium tetraphosphate. These are the normal flocculants to use so that you can thick the mud so it can lift the cuttings properly. And if you want to thin the mud, thinner or dispersant, so if you want to make it thinner, the drilling fluid, you can use this kind of material, which are the tannins, lignoitic material, and various polyphosphates. All of them are available at the rig site. When you go on the rig site, you buy all of them. You don't know what you need in the one. So then sometimes you need the viscosity. When you have a highly porous zone, you need a high viscosity so that the fluid do not go inside the rock formation. So in that case, you are used, the CMC is the most famous one, this carboxymethyl cellulose. It's the most famous one that they use as a viscophier. And they increase the viscosity sometimes. They need it so that the mud do not go here and there a lot. pH also plays roles because there are minerals downhole and they may react with the drilling fluid. So sometimes we have to maintain the pH. So in order to change the pH, again, you can use the lime, caustic soda, bicarbonate soda. These are used to change the pH of value of the drilling fluids. We have to maintain the pH value because the cutting, sometimes the drilling fluid is reacting with the minerals and with the acid or base, or we have to see in the lab what is going on there and which one is reacting with whom. As I said, some of them the fluids can be lost inside the rock. So in that case, we have to do the filtration process so that the cuttings, the drilling fluid should not be lost inside the porous media or somewhere. So in order to do that, we have to use some filter loss additives, which includes the starch and sodium polyacrylate or CMC. So these kind of materials are used for the filtration process. So as you see that we have now lots of properties that we play for the drilling fluid. The first property, density, flocculation, deflocculation, viscosity, pH value, filtration, or emulsions. Okay, this one sometimes may be used to help to lift the cutting, these emulsions, but these are not really the desired quantity and so on. So as we discussed earlier, the drilling fluid, it goes down from here, from this zone, and from here it has had a jetting action, and then it goes back. And what we want, that it should not be lost inside the side areas. It should go straight up and go towards the outside. This is the normal situation we are looking for in this case. And in order to achieve that, we use all those additives, and there are many more actually. Here I just mentioned some of them, not all of them. You can, if you search on the Google, you can find a lot of the. And how you control the, this is the multiplication sign. So it's wrong here, but it's a multiplication sign. 0.052 multiplied by that, multiplied by density. So if you want to, as I said, you control the well pressure, and if some kick is happening, and you know the kick is happening at 2000 psi, and you want a pressure 2200 psi. So based on that density, you can change the pressure. This one is. Okay. This is the formula we just talked about it. Now, let's take an example of this well here. Let's say there's a chance of kick here. Now this kick here, it is happening here at 2000 psi. Okay, and the depth from here to here, let's say, is 1200 feet. So you can find out the density. For example, you want to keep the pressure 2300 or 2400. So what kind of mud density you require? 2400, 0.052 multiplied by 1200 multiplied by ppg. Can anyone calculate for me?
So it's 38.5.
38.5. So in that case, 38.5.
So is it 0.0052 or?
0.05. Okay.
Okay, yes.
In normal case, it doesn't happen like this. In normal case, the pressure at 2000, 1200 feet usually should be around, let me write, maximum is this one. 2000. So is equal to 900. This should be the normal pressure here, but it is abnormal here. It's 2000. It is quite high. We don't encounter at 1200 feet that much pressure. Usually we encounter around 900. This is the normal one, but if it is abnormal, you can say like 1500, 1600. And the mud value usually range from, the typical is from 10 to 14. This 38.5 is not realistic. It was just to show you that how we can find the density of the mud. Now, if you want to increase, the previous density, for example, was 12 ppg, and now you want to increase to 38.5. So you must add at barite. How much barite? There is a calculation for it. How much barite? There is a calculation for it in the books of formula. How much barite is needed to increase the density from this one and this one. So by the drilling fluid engineers actually do this kind of calculation in order to increase the drilling mud, how much barite is needed and how much mud density is needed to control the pressure. So first they find out how much density they need, and then based on density, how much barite they need. They do these kind of calculations there. Any questions from this?
So will the formulae be given in exams?
Yes.
Okay.
Yes. If I give any mathematical questions, the formula usually are given, the details are given. You just have to use your concepts to solve it, not to memorize it. But the question here is now, yesterday I received an email. Probably there's no chance of midterm or final on campus. Okay, that was the email I received, that even for the midterm, they are not sure that the midterm will be on campus. And most probably it will be online. That's the situation as per now, as per the email I received. Okay, now this is the formula, and then we talk about the solid suspension. And solid suspension is needed because if you stop the drilling, all the drilling cuts will go and fall down. So we have to suspend those solids, and whatever rock cuttings are coming, we have that problem. So for that, a gel structure is required, and again for that we have additives. These are some of the functions that we discussed, which is the cool and lubrication. It removes the heat from the bait, which is then dispersed at the surface. Extra lubrication, and helps the power, and these are the nozzles. Helps the bit to rotate, because the bit is designed in such a way so when high pressure fluid come, it helps to rotate this bit faster than at the surface. Of course, there is a rotation from the drill string and rotary table, but this drilling fluid also rotate this motor. Okay. Also, it helps to support the part of the weight of the drill string. These formula we will use in the drill string chapter. Next chapter is about drill string design, and we'll talk about them there, and we'll solve some example also there. So drill string support, it has to support the weight of the drill string also, and so on. Now we will talk about it, the labs, what kind of equipment they use, and how they design these drilling fluids. Now this picture is very interesting here, and imagine this one. If you just take this picture, you should take like this. Now this area here, the drilling mud is returning. So when this drill mud is returning here, when this drilling mud is returning here, I need to learn how to use this. Drilling mud should go is lost inside the formation. Now imagine this is the drilling mud, the direction flow of drilling mud, which is it has to go up, but it is not going up. It is losing inside the formation. So now we have some layers of right side of the drilling fluid near the wellbore. Now, for example, this is the hole. Then the first part is the mud cake that is formed, the thicker wall that the mud cake is generating. Behind that, we have a porous medium. Now, this porous medium has different, you can say, the ratings. Here, the drilling mud is going and creating lots of problems and choking, blocking all of this area. But when you go that, as you go deeper, this one is less filtered, and this one is a total virgin formation, means it is untouched, and there's no effect of drilling fluids inside this kind of a zone. Okay, so there's no fun. But as you go from the wellbore, you go towards the raw formation. There in between, you see that there are number of layers where there is a different amount of filtration has occurred. This is the formation damage. For example, now drilling fluid has gone to this black zone. It has totally blocked the porosity and permeability. So, for example, if there is oil here, it cannot go out. It will be blocked at this point. So this is the total filtration. After this total filtration, there is a small transition period where there is a filtration, but effect is not too much here in this point. And then we have the formation, which is untouched. It has original permeability and original porosity. You see now here porosity is very, very good, and permeability is very, very good. All are very well connected. The effective porosity is also very, very good. But the above it towards the wellbore, there because of the filtration of drilling fluid, there is a major formation losses. And what is our job as a drilling fluid engineer? To avoid those losses. So what we do, we try to create a mud in such a way that it creates a very good blockage here, and mud should not go inside the porous medium and block this oil zone or whatever zone we are going through, or fresh water, for example. As I said that this is the original formation here, and this one is, you can say, the mud cake, this kind of here. But this mud flow, when it comes there inside here, it can cause a filtration problem, and it is cause a formation damage. So now, for example, if there's some fluid here, oil or gas, it will not flow because all is blocked through the filtration. So our drilling fluid has to be designed in such a way that it should not create problem at this point. Now, how to measure the mud density? We have equipment called mud balance. So very simple equipment, not so expensive. We can get it probably in $100, this one. And the mud balance is actually used to find the density of the mud. And after adding the barite, for example, how much barite is added, how much other additive you can add, and change the density here in order to use it in the well-controlled situation. So this is the mud balance equipment that we use. Then these are the additive bentonite, for example, you are using. It has a density, this one, 21.7 per gallon or 910. So we have some formulas to use the density of those muds and to increase the density. Then if you want to change the viscosity, we have a Marsh funnel viscosity. And as you know, sometimes we have to change the viscosity of the mud. So we use this kind of equipment. It's a very simple cone. And based on the time, we have this kind of viscometer. Also, this one is very cheap to buy. So maybe I will recommend university to buy them in the next semester. This one is the rotary viscometer. And the purpose is to check the gel strength, and gel strength is needed to suspend the solids and cuttings. So if you want to add more additives and then you want to check its gel strength, so this equipment is used to find the gel strength of the mud, and this is called the rotary viscometer. Here it is used the rotary. And then we have this one for the filtration and mud cake. The picture I showed you here, this one, we create the same scenario here in this one. So what we do, we put one filter there, okay, and we give it a high pressure, and we see that how much is the mud filter has formed there, and what is the thickness of the mud cake that can be formed here at this point. And we of course use the high pressure cell here for that. Here you see the solids. We have a paper, filter paper, and we are trying to use this drilling mud on it under high pressure. So we want to see that how thick a mud cake can be formed. Here you can see that if you increase more solids, a bigger mud cake can be formed. If you use less solids, uh, less thicker mud cakes can be formed. This is important property to avoid the formation damage and low circulation. We don't want the formation damage and we don't want the low circulation. So for that we need to create a mud cake so that the fluids do not go and lose inside the formation. For that we use the solids, and the equipment that we use in the lab is this mud filtration process that is helped to use this one. This is under high pressure and high temperature. Again, it's a filter press. The purpose is to create a mud cake and mud cake so that we check how much is the thickness of the mud cake in order to avoid the low circulation or any filtration that can cause the formation damage like this one. So we don't want this kind of filtration. So what we try to do, we try to create a mud cake here at the top. And this mud cake is checked here using this equipment under high pressure. We use one filter paper as good as the real rock, and then we try to use the mud under high pressure, high temperature, and see how much mud cake is formed over it so that it can avoid the one. Then we have a simple one which we use to find the sand content. How much is the sand particle size inside the drilling mud. So all these equipments are available at the rig site. Every drilling fluid engineer at the rig site, they have a small lab there and mobile lab, and they do these kind of testing every day. Every 6 hours, they keep checking their drilling fluids by using those equipment and so on. This is the rig to check the pH meter, to check what is the pH is going on. So all these equipments are not costly. Probably if we have $2,000-3,000, we can establish that small lab to detect and develop the drilling fluids and so on. I have personally used them in my previous university in Malaysia where I was doing master. So I was taking the drilling labs there and demonstrating students these experiments there. This is the pH meter. It tells the electrolyte potential generated between the glass and so on. So this is also used to check and then the solid content determination to check how much is the solid content because it affects the mud cake process and so on. And here we have the methylene capacity, reactive clays, and so they check this in order to check if we are using the drilling fluid, it should not react with the mineral down. So they have this kind of mud, so it exchanges how much reaction can occur inside the drilling fluid. Then we have the lubricity. So, and this is aging cell. They put the cell and check that what is the condition after a certain time. For example, if you stop the drilling process, what will happen to drilling fluid? Whether it will get turned to solid, stay liquid, or so on. So they put the sand inside the drilling fluid inside the cell and allow it after some time under high pressure or temperature and see the effect like after some time, what will happen to the drilling fluid, whether it will convert to the solid or stays the liquid. What is the situation of the cuttings. So they have the lab which determines all the properties before they go for the real, and they keep track on those laboratory tests so that they can come out of it. So that was the drilling fluid. It was a three-part. First part we talked about the functions. The second part we talked about the pore pressure and fracture pressure window, and the third part we talk about some of the additives like bentonite, barite, and coolant, and some others, and this one. And now I will, as an extra, I will add some more presentations which will talk about the additives about it. So it's an extra one which will help you to understand what kind of additives are used during the drilling fluid process. And in the next chapter, we will talk about the drill string design, how we design the drill string process. And we have some mathematical questions left for the drilling circulation system. We will talk about them also. So any question? Okay, so today's lecture actually we'll stop it here because we ended up this one, and the new lecture I will start in the new one. So for now, do you have any question from drilling fluids or drilling engineering? Okay. Now today I will post the another presentation for the drilling engineering subject, And I will share some of the research papers that you have to prepare the presentation out of it. That's the presentation number 2 that you have to do next week. Next Thursday, I'm putting it. We have to stick to mostly with presentation and projects. And afterward, after you develop some more concept, then I will give you a project on a software to do that. So for now, we just stick to presentations. Yes. Also, I want to ask you how other lecturers are dealing with the assessments. What kind of assessments they are doing so far?
I don't think they've changed for most of my classes. We still get 2 midterms.
Yes, but midterm is not going on campus also.
Yes, we're all doing it online.
Online, but so what kind of assessment other lecturers have done? A presentation, okay, we did, but what others? How they are doing the exams or something?
Some of them have a lot of like equations to solve, so we do assignments and send it. We get graded based on that.
Only the assignments. I don't like assignments because assignment you can, some of them can go and check and just put $1 and you get it ready.
You can have a system where everybody gets a different number.
Yes. Yeah, projects I will give you. I will not give assignment, but I'll give projects on the software.
Okay.
For example, the next one is Brill string design. So it's a good one. So this can be done in a software, the next chapter. So after that, I will float a project on Brill string design.
Will the software be available?
Yes, I will give you a crack one.
Okay.
Yeah, I have all the crack software, so I'll give you. Slowly, we have still 2 months, so slowly. If I give you everything, in a one shot, then you'll be like, what's going on? So I have to first develop the concept, then give you something so that you catch it, what I'm talking. Okay.